Okay, lecture number 10, ray optics. Okay, so we're going to go back to this guy named Higgins. All right, he was an instrumental physicist related back to his assumptions on light. All right, and so we use his assumptions based on light to go ahead and define a lot of the equations we've already been talking about. Snell's law is actually a derivation from one of Higgins' principles. All right, so Higgins, he assumed that light is a form of wave motion rather than a stream of particles. Okay, so that was kind of contrary to maybe what was the established thought about what light what actually was, as just particles themselves. But he actually assumed that they were waves. Okay, so his principle is a geometric construction for determining the position of a new wave at some point based on the knowledge of the wave front that preceded it. Well, what does that mean? Well, let's think about this. All points on a given wavefront are taken as point sources for the production of spherical secondary waves called wavelets, all right, which propagate outward through a medium with speeds characteristic of waves in that medium. All right, so after some time has passed, the new position of the wavefront is the surface tangent to the wavelets. All right, so let's take a look at a picture of that. So if you can imagine that there are waves traveling this way of light. Okay, what Higgins said is that you take a snapshot of those waves, all right? Let's say this wave is coming this way. At a certain snapshot, there's actually light that gets emitted in every single direction at that point, all right? And this happens every single point of that wave, all right? So every point along that ray that we were talking about there, we get this emanation of light from every particle, right? So we call those waves from every particle, we call them wavelets, okay? So after the wavelets have moved a certain distance, all right, and these wavelets, they will travel in the same medium at the same speed that the original ray is actually traveling, all right? And so you could also say that those wavelets are also emanating their own wavelets as well, all right? So every point along the ray that's coming out of those wavelets are emanating their own points. So it can get kind of complex very quickly, but we're just going to be talking about a single point essentially, and analyzing a few points at the same time, so it doesn't get too complicated. But if you say a certain time after this snapshot was taken, A prime was taken the first snapshot, and you say a certain time after that, and we multiply that time by the velocity or the speed of that light in that medium that we're talking about, let's just say air, for example, that would be the speed of light, all right, that we know of, and we could say that it traveled this distance. The distance from here to here is c times delta t, right? And we actually see a new wavefront. So it really propagates this wave in the same direction, right? Everything's moving at the speed of light in every single direction, okay? And so we can understand we have, the continuation of the wavefronts. Okay, so this is the old wavefront at some certain snapshot here, and the next wavefront, all right, is just at another time, some delta t later, and that would be a new wavefront that's going on. All right, what about a spherical wave? Let's say that we have some point source of light, maybe like a light bulb, and we have rays emanating outwards of that. Right? Well, in a similar fashion, we have the wavelets that start at these individual points and they emanate outwards as well. All right, so we have an old wavefront that was circular. This is in a two-dimensional situation. Old wavefront that's circular, and we have the new wavefront that is also circular. All right, and then the distance that was traveled, okay, once again, is at c delta t. It's the amount of time that we're talking about times the speed of light in that medium to go ahead and find out the distance between the old wavefront to the new wavefront. So the new wavefront is tangent at each point to the wavelet. Okay, so you see the tangent aspect. The wavefront is tangent to the wavelet after a certain amount of time. All right, so using Higgins' principle and the law of reflection, remember this was a pretty easy law. We said for a reflected ray, we said theta 1, which is the angle between the normal and the ray, is equal to theta 1 prime, which is the angle on the other side, theta 1 and theta 1 prime right there. So that's what we said, but how do we actually go ahead and prove that? All right, well, this is not very difficult. So if we have two rays that are coming from the same source, right, which means not only are they coming from the same source, they're traveling with the same speed and they're parallel to each other. All right, so imagine there's some kind of light bulb over here, or maybe the sun, and we're just analyzing two of those rays. So let's remember, we can't assume this just yet. We're trying to prove that. Okay, so if we see ray 1 that's going to A and bounces off at some angle, and we'll call that angle gamma prime. Okay, here's ray 2, and ray 2 goes through point B, goes to point C, and the angle that it makes with the horizontal is going to be gamma. Okay, so basically, if we can prove that gamma and gamma prime are equal to each other, then we could also say that theta 1 and theta 1 prime are also equal to each other. All right, because we see gamma prime plus theta 1 prime is 90 degrees. Okay, and if we could somehow make these guys equal to each other, well, then that means we would have a gamma right here. All right, so what do we know? Well, at point A, we notice that there's going to be a wavelet, right? And so the wavelet will kind of follow this path here from A to D, okay? That wavelet travels a certain distance in a given amount of time, all right? And that would be the distance A to D right there, all right? So we still don't know what this angle is or how it's related to any other angles there, but we just know it bounces off, and A to D, the ray travels a certain distance in a given amount of time. Now, in the same amount of time, and at the same point, so when A released its wavelet, B released a wavelet as well, okay? But that wavelet is centered about B, so we notice that if the ray continues on, right, that distance BC has to be equal to distance AD, because we're talking about the same amount of time, same speed, so it has to be the same distance traveled, all right? So we know AD is equal to BC. Okay, that's easy. If we also say, I know that there is a 90-degree angle between some blue line that you see from B to A, there's a 90-degree angle between the blue line to DA as well, right? So that makes things relatively simple for us. So we know that if BC and AD are equal to each other, these 90-degree angles obviously are exactly the same, and we can essentially make a nice right triangle. Right? You see there's two right triangles, A, D, and C, and then A, B, and C, they're two right triangles. What do they share? They share AC. All right. So just think about it. If I have two right triangles that have the same side, actually two of the sides are exactly the same, right? BC is equal to AD, and both share the side AC, and then also one of the angles is exactly the same, 90 degrees, all right? That means that these two right triangles are congruent. They're exactly the same. So if I know that, that means whatever this angle is, gamma prime has to be equal to gamma, all right? And so basically we proved that since these two triangles are congruent, all right, whatever this angle is right here has to be the same thing as this angle because it's the same orientation, right? This is the angle across from the blue line for DC, right? This angle right here is the angle across from BA, the blue line, right? And we already said BC, right? And AD are the same, so that means that BA is equal to DC, all right? So we could also say that. So if that's the case, since gamma prime is equal to gamma, all right, and that essentially means that we know that 90 is equal to theta 1 prime, all right, plus gamma prime, all right. That essentially means we could plug things in pretty easily, okay. So theta 1 prime is equal to 90 minus gamma prime, okay, and that means theta 1 has to equal 90 minus gamma. Okay, so that's pretty easy, all right? All we need to do is essentially plug in for both of them, all right? And so we can get a 90 minus theta 1 prime is equal to 90 minus theta 1, just from this expression right here, rearranging this equation, all right? And so all I need to do is subtract 90 from both sides. There goes the 90, multiply both sides by -1, and I get positive on both sides. So we've proved Higgins' principle, all right? Keep on going here. This is essentially just it's just allowing us to make the derivation one more related back to the congruent right triangles. All right, so cosine gamma is BC divided by AC, and this is using cosine. Cosine gamma prime is AD divided by AC. These two triangles are congruent to each other. That means the cosine of those angles are exactly the same thing, all right? Since we know that BC and AD are exactly equal to each other. That means gamma is equal to gamma prime, and then we just showed that theta 1 has to equal theta 1 prime. This is the law of reflection. All right, now let's go to the law of refraction. Okay, we said that was related back to Snell's law. So we had n1 times the sine of theta 1 is equal to n2 times the sine of theta 2. Seems like a pretty easy expression, but we need to figure out where that actually came from in terms of a derivation of that. Okay. So how can we do that? Well, once again, we have something very similar to the reflection derivation, where we have two different rays, right? Ray 1, ray 2. They hit, one ray 1 hits point A. The second ray is going to hit point C, but we're going to look at wavelets at point A and B, because that's when we can go ahead and take a snapshot and they emit wavelets at the same time, A and B do. All right. Now, when we take a look at the wavelet at B, all right, we could say that let's imagine we let the wavelet travel the same distance from B to C. Okay, so that took a certain amount of distance. We'll call that the speed of light times the delta t that it took to go ahead and travel from B to C. Okay, now inside this material, this glass, right, we know that the speed of light is going to be different. It's going to be slower. So the wavelet that started at A doesn't get as far as from B to C. It goes from A to D. It's a lot shorter. So this is some speed, right? We'll call that that slower speed, if you will. Okay, and maybe we can call it V2 in the same amount of time. That's that distance, A to D. Okay, so A to D is equal to V2 delta T. Let's actually change this to V1 because this doesn't have to be air, right? But V1 times delta T, that is the same thing as BC, all right, B times C. Okay, so BC is equal to V1 times delta T, right? So this is not too difficult, because we notice that these two right triangles that we see here, once again, we draw a blue line which is perpendicular. That means this is a 90-degree angle, right? These two lines are parallel, 2 and 1 are parallel, so B and D will be directly connected to each other at 90-degree angle, all right? And we do the same thing for D to C, okay? So we see this light refracts into this material. This ray reflects into this material. That means if I draw a perpendicular line here, all right, there's a 90-degree angle here, and it connects D directly back to C, all right? Okay, so if we go ahead and take a look at that, and also another way to also think about that is that we know that the light traveled from A to D in this amount of time, that delta T, all right, and the light right here traveled from B to C in that same amount of time, all right? So it travels faster, travels slower. So when I draw a perpendicular line, we have to be connecting D directly to C. Okay. All right, so let's do some, so now that we have two right triangles there, let's do some sine aspects here. Sine of theta 1, okay, we're calling theta 1 the angle between the horizontal to the blue line. Okay, so sine of theta 1 is equal to BC divided by the hypotenuse, which is DC. All right. Now, what's another way to represent BC? Well, we have V1 delta T divided by DC. All right. We have sine of theta 2, which is the angle between the horizontal to the DC line. All right. Sine of theta 2 is equal to AD divided by DC. Opposite over hypotenuse. So AD, the distance, that's V2 times delta T, divided by the hypotenuse, which is DC. All right, so maybe you know what we're going to do now is just go ahead and divide these guys into each other. Sine theta 1 divided by sine theta 2 is going to equal V1 over delta T divided by DC, and then V2 over delta T divided by DC. All right, DC's cancel out, delta T's cancel out. This is equal to V1 over V2. And now we're almost done. Because if we remember, N is equal to the speed of light in air divided by the velocity, right, of that light in some particular medium. All right. So this could be air, the C could be air or vacuum, right? We get that idea. So if I just try to solve for velocity, velocity is equal to speed of light divided by your index of refraction, N. So let's go to the next slide, see all this stuff being put together here. All right. So we already made these relationships, sine theta 1, sine theta 2. And we go ahead and just go to the next one because this exactly says everything that we just did. All right. So sine theta 1 over sine theta 2 equals V1 over V2. All right. So that means V1 is equal to the speed of light, right, in a vacuum situation divided by the index of refraction in that first material. V2 would be defined similarly. C divided by N2. All right. So we just go plug them in. That's what you see right here. All right. Sine theta 1 equals sine theta 2 is equal to C divided by N1 over C divided by N2. The C's will cancel out. N2 goes to the top and N1 goes to the bottom. And there's Snell's law for you. Just bring N1 up to the front on the other side. All right. Up to the top, I should say. Sine theta 2 can come over to this side and you're left with Snell's law of refraction. All right, so we can't just use these equations and just say, oh, we don't care about where they come from. They do come from some kind of explanation, and Higgins' principle actually tells us where Snell's law comes from. All right, so for a given material, the index of refraction varies with the wavelength of light passing through that material. All right, the dependence of n on lambda is what we call dispersion. All right, so Snell's law indicates light of different wavelengths is bent at different angles when incident on a refracting material. Right? Now, if that wavelength is different for different waves of light, right? Well, then that means it's also going to go ahead and bend at different angles. Right? So up to this point, the waves that we've been talking about have only they've been coherent, which means they have the same wavelength, right? And they kind of go step by step in the same direction with the same wavelength. But if we have different wavelengths, well, then we actually get different angles for that refracting material. So here we go. If we take a look at the different colors of the rainbow, all right, and for different materials, you'll notice that you have different index of refractions for different colors, all right? So in this particular case, when we're looking at crown glass or acrylic or fused quartz, you notice that the wavelength is smaller, right? Obviously, the wavelength for different colors are smaller, right? Violet has the smallest wavelength. And we go to red, which has the largest wavelength, right? You notice that the index of refractions are starting to decrease on us, right? Which means that the colors more on this side actually bend more through glass or through some other material that is not air. All right, so if the light is going from air to some other material, well then we have more of a bending, and we have less bending for the red. All right, so violet bends more than red light when passing through a refracting material, and that's essentially is what it's telling us there. If we actually use a prism to help us bend the light, right, we actually get two bendings going on, right? Light will enter from one side of the prism and then exit another side of the prism, or you can do it on the bottom here. It will enter on this side and then exit on this side on the bottom, right? And you notice that the double refraction or the two refractions that happen allow the light to actually get split up, right? So you notice that we said that the violet and colors that are closer to the violet get bent more. So that's why you see a thicker line for more violet colors. The red line is narrow, so it didn't get bent as much. All right. So the violet deviates the most, red deviates the least. The remaining colors obviously are in between. But we do see red on top, violet on the bottom in this case, and that's because of the amount of angle of deviation that's going on. Right. The violet actually, even though it's thicker, is on the bottom, which means overall it bent more. Red is thinner, but we can see it's on the top, so it didn't deviate as much. So this takes us to the rainbow and understanding what causes a rainbow after a storm. All right. So basically what's going on here is a ray of light strikes a drop of water in the atmosphere. It's like the drop of water acts like a prism. Right? What happens there is it undergoes reflection and refraction. Okay, the first refraction is at the top of the drop, and we'll see a picture in just a little bit. And the violet light will deviate the most, red light will deviate the least. So let's take a look at that. So imagine sunlight. All right, one of those rays of sun is going to go ahead and hit a drop of water. Okay, so what happens is we get refraction going on right here. Once again, what did we say? We said violet gets bent the most. All right, red gets bent the least, still bending though. Right? And so what happens is it bounces off, it reflects off of the back of the water droplet. All right? There'll be some light that will pass through it, right? But we actually get this bending back. The water droplet kind of acts like a mirror. Okay? And so when it comes back, now you notice that red is actually on the bottom, violet is actually more on the top. Okay, so the angle between this original ray to the two different colors, 42 degrees is a bigger angle because red actually ended up on the bottom. 40 degrees is a smaller angle because violet ended up on the top. Right? But it's because of refraction here and reflection over here. Okay? So the angles are given to us right there. Which brings us to a certain question, and on the next slide you'll get the answer. But when you look at a rainbow, right, knowing this is happening right here, what's the first color, or what's the color on top of the rainbow? All right, and so hopefully, if you can imagine that you're standing right here, okay, if you're standing right there, all right, the color that's going to hit your eyes first, right, actually is going to be red, okay, because violet's going to go over your head, okay, and that means violet is actually going to be on the bottom of the rainbow, because violet's going to be the last color that's going to hit your eye. Okay, so got to be careful what this actually means. It doesn't mean violet's on top and red is on the bottom. Actually, it's reverse. It's what your eye perceives. Red is on the top and violet's actually on the bottom. So this is what we have right here. Red is on top, violet on the bottom, right? Because that red hits your eye at however tall you are, right? And violet goes over your head. Right? But when you go down the rainbow, violet is the last color to hit you because the red is hitting somewhere below and not into your eye. Okay, so the red ray is seen. Drop lower in the sky would direct violet light to the observer. The other colors of the spectra lie in between, obviously, the red and the violet. And so you've probably heard or seen a double rainbow. Right? You can actually do this very easily with the mist of a hose. And what's going on here is that reflection that's happening inside the water droplet is actually happening twice. Right? So if this is the water droplet right here, right, we have refraction going on right here. Right? Then we have refraction, then reflection, okay? And then refraction again, because that light will come out, but then it will reflect one more time and then come out over here, okay? So you get a rainbow here and you get a rainbow essentially there, okay? From the different colors that are actually going on there. And this can actually bounce again. It won't be a very bright rainbow that comes off, but you could have a triple rainbow possibly, all right? But you do notice that from one rainbow to the other, the intensity of the second one is a lot lower, all right? That's going on. And you also notice their colors are reversed, all right? From purple on the bottom, red on the top, as we mentioned before. Now we have red on the bottom and purple on the top for the second order double rainbow. All right, so the next topic is total internal reflection. All right, this is a phenomenon called total internal reflection, which means that light is directed from a medium having a given index of refraction toward one having a lower index of refraction. Right? And if it's totally internal reflection, means that the light will actually stay inside of the original medium. Okay, so what does this really mean? So here we go. If we have possible beam directions, right? Obviously, if I have a beam starting inside, let's say, a piece of glass, you put a light bulb inside of a piece of glass and go ahead and shine it. If that, or we have a ray of light going straight up, well, there's going to be no angle change. It'll actually, this light will speed up when it gets into the air, right? So we know this from Snell's law. Okay, we expect that theta 2 is going to be a bigger angle than theta 1 because n1 is actually bigger than n2, as according to this. Okay, so it's slower here, faster here. We get a bigger deviation for theta 2 than theta 1. Okay, same thing happens for another ray. Let's see where is theta 1 for this guy. Theta 1 is right here. All right, and theta 2 is right here. So once again, theta 2 has a bigger angle than theta 1. Okay, and we have another theta 1 here. And what we get here is theta 2, but you notice in this aspect, theta 2 is actually perfectly 90 degrees because this ray 4, when it comes into the air, actually just follows the boundary of the glass right there. Okay, so that means you notice that theta 2 is getting bigger, 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 and then for ray number 5, the light doesn't even make its way out. It actually stays within the material. Okay, so that's important. And what does this really mean? Well, let's use Snell's law. When do you get total internal reflection, which means, once again, the light stays within it? This is kind of like the boundary point, right? So if that happens, then we know that we have total internal reflection, essentially, that the light is staying within the material. That's kind of like the boundary aspect, right? So sine theta 1 times n1 is equal to n2 times sine theta 2, right? And so where did we start? We started in n1, okay? Sine theta 1 is whatever angle we need to go ahead and shine, with respect to normal, to go ahead and shine up to into the air, right? So we'll just call that theta 1. Now what's n2? n2, as you can imagine, is just going to be air for this situation. So we can call that 1, right, for n2. Now sine theta 2, that's pretty easy because for ray number 4, sine theta 2 is a perfect 90 degree angle. So that's just 1 times 1 in this case. All right. So this n2 can be any substance really, right? It's just that n2 has to be smaller than n1. Okay, but you do notice that the sine of theta 1 is equal to 1 over n1. Okay, if this is an air. If this material is, if n2 is not air, well then let's just call it n2, all right, divided by n1. Okay, so what is this special angle? Well, it's just the inverse, right, of n2 over n1. At this angle, anything that is, let's think about it, this angle is getting bigger, bigger, all right? And obviously theta 1 right here is the biggest it can be of all these examples here. So if you are above theta 1, well then you know that you have I'm sorry, let me take that back. If you're above theta 1, all right, when theta 1 equals the inverse sine of n2 divided by n1, then you know anything above that will be totally internally reflected. All right, that's exactly what we just derived right there. Okay, so this angle of incidence, that angle, that theta c right there, is what we call the critical angle. Okay, we just know that you go above that angle, you'll be totally internally reflected. If you are at that angle, if you are at theta c, in terms of the angle that you shine this light from the glass to the normal, right, then you have this light traveling along the edge or the boundary. But if you go above theta c, well then you will get this situation. You'll actually have a reflection going on. All right. And that should be easy. If it's going to reflect, well then this will be theta c as well. Okay. Okay, so for angles of incidence greater than the critical angle, all right, so let me go back real quick. So imagine if this is theta 1, for example, then this is theta 1 right here. Okay, don't call it theta c because theta c is only for this ray right here. So for angles of incidence greater than the critical angle, the beam is entirely reflected at the boundary and still obeys the laws of reflection. Once again, those angles have to be exactly the same. So total internal reflection occurs only when light is directed from a medium of a given index of refraction toward a medium of lower index of refraction. So this doesn't happen when you're going from air into something else. This only happens when light is starting inside of a material and then trying to get to air. All right, so you can't just make this situation anytime. Now, how can we use this to our advantage? All right. Well, something that's kind of interesting here is if you actually try to make a difference or try to distinguish diamond versus cubic zirconia. With the naked eye, it's hard to do that. You can't really tell if diamond and cubic zirconia are different than each other. All right, but people can actually use things like corn syrup, all right? And so diamond has an N value, so just the N of diamond, all right? Index of refraction of about 2.42, all right? Cubic zirconia, NCZ, is about 2.2, all right? So obviously diamond has a bigger index of refraction, all right? But, you know, they're kind of close to each other, relatively close in that case. So, which means that, you know, when you look at the light bouncing through these two materials, right, you might not see any particular difference. But if you go ahead and put both of these things in corn syrup, right, corn syrup has a medium index of refraction, right? Corn syrup is equal to about, let's say, about 1.5, all right? Okay, so what happens here is that if you actually, you know, the liquid form of corn syrup, go ahead and put the cubic zirconia in the corn syrup, you'll actually get less refraction going on, all right? Because this corn syrup index of refraction is actually closer to the 2.2 than it is to 2.4, all right? And this is how you can distinguish. You could actually see more light, right? Or, you know, when you look at a diamond, right, it's glistening. So when you go ahead and put both of these guys into the corn syrup, right, you'll actually see the diamond glistening more than the cubic zirconia, right? Because you've changed the environment of index refraction, basically, right? The cubic zirconia is not allowed to bounce light as much or bend it as much as the diamond is compared to the corn syrup. All right, so, and if you can get a liquid form, and you can't really get too high for liquids. It's hard for it to get close to 2 or above 2, but you try to get a liquid that's relatively high, and you'll notice a bigger difference between the cubic zirconia and how light bounces through it and the diamond. So let's go ahead and take a look at an example, a view from the fish's eye. Okay, so for this example, we're going to go ahead and try to find the critical angle for our air-water boundary. Remember that the index refraction for air, all right, is going to be 1, all right, and then the index refraction for the water, all right, that's going to be 1.33. Okay, so if we go ahead and use our equation, which is the sine of the critical angle, all right, is going to go ahead and equal the index of refraction of the second substance, right? That would be air in this case, because we remember that the light or the light source is actually inside of the water in this case, all right? And this would be N of the H2O. This would be N1 because that's where the light is emanating from. So it's pretty easy. You got 1 over 1.33. Right, and when you solve for your angle, the critical angle, essentially doing the inverse of sine, all right, of 1 over 1.33, we should get a 48.8 degrees. All right, and so critical angles are critical, or for lack of a better word, right? They are useful for fiber optics, right? Because what is fiber optics all about? Well, it's all about making sure light travels from one end of a fiber optic cable to another end. Fiber optics are just essentially pieces of glass. They could also be pieces of plastic, right, that allow light to travel through them, okay? And really, all you need is a detector on the other side of a fiber optic to detect if light is being received or not being received, and that can be easily transferred into ones and zeros, basically on and off, okay? So basically, you're piping light from one place to another, okay? You're trying to get, and this can be flexible glass and flexible pieces of plastic that can do this, so it allows you to put cameras inside the human body to go ahead and take a look at different things. Telecommunications most definitely utilize fiber optics because it's a very convenient, relatively low cost way to go ahead and get reliable data, all right? So you think about electrical signals, and obviously we have telecommunications that use electrical signals, but you know, sometimes that's not always the most convenient or cost efficient or even energy efficient way to go to communicate things in terms of sending electrical pulses, all right? If we can send light pulses that can be deciphered into ones and zeros, that's a lot easier. All right, so flexible light pipe is called optical fiber, all right, and maybe you've seen these before, maybe at a theme park or something like that, all right? So you're just putting light on one end, and that it's hard to see the light actually traveling through the pipe, but on the other end, it gets illuminated, all right? Essentially, it's hitting the end of the other pipe, and that can be easily detected by some kind of light sensor. All right. What goes inside of or goes into creating an optical fiber, all right? Typical optical fibers are not just glass that are exposed to air. Right? We want to make sure all that light actually does stay inside of the fiber optic. All right. So to assist with that, we typically like to put a cladding around the glass or plastic core. All right. So the cladding has a lower N value than the core. Probably not, obviously not going to be as low as air, but it's going to be relatively low. All right. So if that's going to happen, and as long as we shine light at a relatively big angle with respect to the normal, right, then all of that light's going to be internally reflected, and it's just going to bounce off the sides all the way down, right? And we'd like to put a jacket around things just to make sure that no light essentially is escaping there. But the cladding is the important thing right there, that's exposed to cladding. All right, so switching gears here and going into mirrors, and then later on we'll talk about lenses for the next lecture, all right? But now we're using the rays of light to go ahead and bounce off things like mirrors, and then eventually they'll go through things like lenses, all right? But we can understand for mirrors, we have images and we have objects that make images inside of the mirror, okay? So to help us really understand where those images are going to be, I mean, it's pretty easy if you're just looking at at a mirror that you might have in your house, all right, you see if you look at yourself in the mirror, you see yourself a certain distance behind the mirror, right? That would be the image. And you know the object is yourself right in front of the mirror, okay? So to help us really get into the mathematics behind this, we need to denote certain letters here, all right? We have the object distance, all right? That's the distance away from a mirror or a lens, and we'll get to lenses later, but the distance away from the mirror that the object is. That would be denoted by the letter P, all right? The image distance is the distance between the image and the mirror or the lens, and that would be denoted by the letter Q, all right? So what do we do with this? Well, we have something called the lateral magnification, okay? For a regular flat mirror, we should probably already know the lateral magnification, which is the ratio of the image height to the object height. That's easy for a flat mirror because that's just going to be 1, right? We've got the same height of that image as the object itself. But we're going to denote that lateral magnification, and really we're just talking about heights right here by the letter capital M. All right. So images are always located by extending diverging rays back to a point at which they intersect. All right. That's where images come from. So now we really get into the, rays of are essentially just arrows that are hitting a mirror, and they can look like they go through the mirror, right? According to our eye, right? But we're essentially like those rays are actually tricking our eye to think that something might actually be inside of the mirror. Okay. So images are located at either a point from which the rays of light actually diverge or at a point which they appear. And this is important. They actually diverge or they appear to diverge. Right? So we'll see some images that allow us to really see this. Okay? First of all, a real image as opposed to a virtual image. A real image is formed when light rays pass through and diverge from an image point. All right? So these are points, or these are images that can actually be displayed on screens. All right, so if we look at an LCD projector that typically is in any classroom, those are images that are actually displayed on a screen. So that really means that light is actually converging. If it's in focus, they're converging right at the screen. Right? But sometimes you have an image, and this is what a mirror does. A mirror makes a virtual image, all right? The image that you see, if you put a screen behind the mirror, you're not going to get any image, right? Because it looks like there's an image there, but there's not really actually an image because light rays are not actually going to that point, all right? So they just appear to diverge from that particular point, okay? So virtual images cannot be displayed on screens. So let's go a little bit further into this. What does this mean? Well, here's a flat mirror, all right? If we have rays of light that are coming off the object, right? And we're looking at that thing in the mirror. So here's our eyes. Those rays of light that are coming off the object, they go into our eyes, all right? But we trace these rays back, all right? So they're going into our eyes. We trace it back and we see the object in the mirror. Not the object itself, because we're not looking at the object, but we see the image of that object in the mirror. And it looks like the it looks like the object is inside the mirror a certain distance away back, all right? But this is what we call a virtual image because the rays of light don't actually converge here. It looks like they do, but they don't actually converge there, all right? So it's an apparent conversion, or converging, I should say, of those rays of light back to the image right here. All right, so flat mirrors are very easy. We see P right here and Q. P and Q are exactly equal to each other in this image here, all right, or this entire picture here. Okay, so the P is the distance between the mirror to the object. Q is the distance between the mirror to the image, all right? And we see all the angles on either side are essentially exactly the same, okay? So this image that we have is virtual because, once again, these rays of light are not actually converging back to eye. They bounce, they reflect into our eye, and it's kind of tricking our eye to think that there's an image, or I'm sorry, thinking that there's actually an image behind the mirror. All right. All right, so a flat mirror always produces a virtual image. Geometry can be used to determine the properties of this image. there are an infinite number of ways or choices of direction in which light rays could leave each point on the object. So if I go back real quick, we just chose 3 that are just coming off and kind of being directed towards the eyeball, right? There's actually rays of light going everywhere, but we don't need to address all those rays of light, right? We just want the few that go into the eyeball. All right, 2 rays are needed to determine where an image is formed, right? So we used 3 on the previous image, but we just need 2. If they converge, then we can say that there's either a real image there or it's a virtual image. All right. So flat mirrors, very easy. Let's imagine here's the object. We could just say it's you, or just whatever height of some object is. We're looking at the rays that are coming off the top of that object there. All right. So if I look at a ray P, right? I'm coming off of P, point P, going flat, going horizontal, hits the mirror, comes right back. All right. Let's look at another ray. Starts at the top, goes right towards the ground, right, and it bounces back, reflects over, or reflects downwards, I should say. So if I just continue this apparent line, right, dash, 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 all right, this continuation of this bounced off ray, dash, 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 all right, we get a height of the image, which is pretty easy. We see H prime and H exactly the same thing, right? According to our angles, if this is theta, this is theta right here according to reflection, all right? We know that this has to be 90 minus theta, all right? Which means that this has to be theta, okay? And once again, we're going right back to it, all right? There's a nice reflection that's going on here because of the mirror. That means that this has to be theta, this has to be 90 minus theta, which means that this has to be theta as well, all right? So everything's the same. P equals Q, this theta is equal to this theta, the heights are exactly the same, all right? These triangles are congruent, P, Q, and R, and P prime, Q, and R are exactly congruent with each other, which means that the observer would trace the 2 reflected rays back to P prime, all right? P prime is the point where the rays appear to have originated. The image formed by an object placed in front of the flat mirror is as far behind the mirror as the object is in front of the mirror. So the overall magnitudes of P equal the magnitude of Q. All right, so when we get back to lateral magnification, this is the ratio of an image height to an object height. All right, so just how much are we magnifying a particular object? All right, so the magnification is defined as image height over object height. That's the same thing as the H prime over H. Okay, so this is general magnification for any type of mirror, not just a flat mirror. We're going to get into concave and convex mirrors in just a little bit. All right, but it's also valid for images formed by lenses, because telescopes and microscopes use lenses to go ahead and give us a certain magnification of the objects that we're trying to look at. Right? Magnification does not always mean bigger. You can demagnify something. You can increase or decrease the size. All right? So M can obviously be less than or greater than the value 1. The lateral magnification is actually positive 1 of a flat mirror, which means that H prime equals H, and the positive sign means that the object is upright, right? When you look in the mirror, you're not upside down, you are upright. But in different types of mirrors, convex, concave, maybe the image actually does flip on you, all right? So positive sign means same orientation as the object. When we're looking at a flat mirror, sometimes it looks like, you know, there's a left-right reversal of it. Like, you put your hand in the mirror, there's like, you know, it turned your right hand into your left hand, all right? That's not exactly true, right? It's apparent, it apparently looks like you flipped your hand basically, but what's exactly going on is that it's actually a front-back reversal, which means that light rays are just bouncing off whatever is in front of it, right, going forward to the mirror and then reflecting back from it. All right, so that's what the mirror image actually is. It's not you know, making things that are on the left go to the right. It's actually just giving you a bouncing of front back. right? Which means light rays are going forward towards the mirror and then reflecting back from it. All right, just to summarize all we have for the flat mirror, all right, not too difficult, is that we have the images as far behind as the object is in the front, all right? So that means P is equal to Q. Right? The image is unmagnified, which essentially means that the magnification M is +1, and it's also the same orientation, which means upright. The image in a flat mirror is virtual, means that you can't actually put a screen there to make an image on some kind of piece of paper or a screen. The image looks like it's there, but it's not actually there. Right? It has the same orientation as the object, and then there's a front-back reversal in the image. So how can we apply this in some kind of situation here? Well, this is what we have when you have auto mirrors. All right. Sometimes you actually just adjust mirrors to get the glare out of your eyes on, especially during the nighttime. Right. When you're looking in your rear view mirror in your car, and you get a lot of glare that's coming from people that have their high beams on. You want to go ahead and use the auto setting to go ahead and try to get rid of that glare. Well, essentially it uses mirrors and it uses a refraction to go ahead and try to get as much glare out of your eyes as possible. Doesn't mean that we want to get everything out of our eyes, right? We still want to see the cars that are coming at us or driving behind us, but we want to kind of reduce the excess bright light that's going to be there, right? So let's think about this. There's a daytime setting for your mirrors, and there's a nighttime setting for your mirrors. And essentially, the difference between them is that a mirror is actually not just a mirror. It actually has refracting material in front of it, like a piece of glass or a piece of plastic. And behind that is the actual mirror itself, right? So the daytime setting, you notice a certain angle kind of bent towards the driver. The nighttime setting, you see the angle kind of bent a little bit backwards, all right? So what's going on? Incident light is actually going into the mirror, the glass in the mirror, right? Now we have two different types of beams that are actually in that incident light, all right? We have bright light and we have dim light, okay? Dim light is obviously not very intense, so when it goes through the mirror, all right, or when it tries to go through the mirror, it's going to have a hard time kind of coming back to our eye, and we're not really going to be seeing it very much. So what happens with that dim light is it actually bounces right off, all right? So it reflects right at the refracting material, all right, at that surface right there. But bright light, right, since it has a higher intensity, then there's more. Basically, bright light just means there's just more rays in that light. Those rays of light actually make their way through the refracting glass, all right? That basically have a better chance of making it all the way through and bouncing off. And they bounce off, and the angle is such that the bright light actually does make it into your eye, all right? Because we want bright light to actually come into our eye during a daytime setting. This is how we can distinguish certain colors from other colors when there's a lot of light out there. We want things to be really bright so we could actually distinguish a lot of light things from each other, all right? If we just had dim lights, and it's going to be very hard to see all the nuances that are out there, all right? Now the nighttime setting, we should notice right here, is that the light goes into the mirror, into the glass. The dim light bounces right back into your eye. And you notice the bright light makes its way through, bounces off the mirror, and then just goes in some other direction, all right? So in this case, we just want dim light to actually go into our eye, because bright light, we don't want that to, produce a lot of, a really bright image in our eyes, right? Something that might not tell us what's actually behind us, right? Or give us some false image of what's actually going on there. The dim light is going to be great, is going to be good enough because it's already dark outside, all right? So as long as we have some light, even though it's not as high intensity as the bright light, it's still enough to go ahead and distinguish what's going on behind us, all right? So it's a very useful application of using refraction and reflection, especially when we're driving. All right, last things we're going to talk about are spherical mirrors. This is where we get into concave and convex types of mirrors. All right, so a spherical mirror has the shape of a section of a sphere. Very easy. All right, we're just going to be talking about really sections of a circle because we're going to do 2D in this case. All right, but the mirror focuses incoming parallel rays to a particular point. Okay, a concave spherical mirror has the silvered surface of the mirror, basically the side that's actually going to bounce light, all right, of the mirror on the inner or concave side of the curve, right? So imagine light is coming in this way. This would be a concave mirror because light's going to bounce off. The silver side is this side of the curve, all right? And so this would be a concave. Convex would be that light is hitting this side of a mirror, okay? The silvered side is on the left side here, okay? So that'd be a convex. The silver side is on the outer or convex side of the curve. All right, so here's a concave mirror, right? Light is going to be entering from this way, all right? And it could be entering at different angles, but we're just going to enter it this way. What we see here is, first of all, let's start with the radius of curvature. It's easy. Radius of curvature is just what's the center of that circle that this mirror is corresponding to, right? The center of curvature is point C. Radius of curvature is just R, all right? Point V is the center of the spherical segment, also could be called the vertex, right? So if you draw a line from C to V, that's called the principal axis. Easy definitions that are going on here. Right, we only use rays that diverge from the object and make a small angle with principal axes, all right, with the principal axis. Such rays are called paraxial rays, all right? All these rays reflect through the image, all right, point. And so basically we only want to talk about a limited number of rays that are, related back to this particular point here, okay? So rays that are far from the principal axis, so you notice that certain rays, when they go ahead and start from an object or some source, all right, and they go ahead and bounce off the concave mirror in this case, they come back to a certain point, all right? So those rays bounce off here, come back to this point right here. But there's other rays right here that bounce off and come back to a point right here, okay? So if you're trying to focus all these rays of light at a particular point, right, some of these rays are actually far from the principal axis, and they would produce a blurred image because they don't all come back to the same exact point, right? We want rays that actually do that. They all come back to the same point, right? Paraxial rays. If we have this is what we call a spherical aberration, right? And to actually eliminate this, we could actually create more of an ellipse for your mirror, all right? Or we just choose rays that are closer to the principal axis. All right, so if we look at an image formed by a concave mirror, this is actually not very difficult. We use two rays, all right? One is going to start at the height of an object, all right? And one ray is, and so let's take that one ray. That one ray is going to go ahead and be pointed directly at the vertex. Okay, so if it goes right to the vertex, reflection still is in play. It made an angle with the principal axis of theta, well then when it bounces off V, it makes the same angle theta off of it. All right. Next up, take another ray and we have it pass right through the center. All right. If it goes right through the center, well that means when it hits the mirror, it comes right back to itself. Okay. And so where's the image? The image is where these two rays intersected each other. Okay, and this would actually be called a real image because there are actually light rays that are there. So if you put a screen right here, you would actually be able to make an image because the light rays do converge there. Okay, so what do we get in this situation here? All right. How can we compare H to H prime? All right. Well, it's actually pretty easy because if we know that the lateral magnification is equal to H prime divided by H, right? We've already said that. We just want to know what's the magnification of H compared to H prime, okay? So if you knew those heights, magnification would be pretty easy to find. But maybe we could also put it in terms of P and Q, all right? And that's pretty easy because we see a right triangle here, right? Right triangle, O to this point, let's call that A, all the way to V, okay? And we see that P is this bottom part of the right triangle right there. We see another right triangle, right? Which is, let's call this point B to I to V, all right? So when we go ahead and essentially compare these triangles together, we see two angles are exactly the same, right? So these are similar triangles in this case, right? So if they're the same, so similar right triangle, same 90-degree angle going on here, same angle theta for both of those triangles, right? That means that this angle right here, we'll call that 90 minus theta, has to be the same thing as this angle right here, all right? So if that's the case, that just means the ratio between h prime and h has to be the same thing as, because q is for the small triangle, h prime is for the small triangle, and p is for the big triangle, all right? But in this situation, you'll notice there's a negative q over p, and that's because the image actually got flipped, right? We started with a certain object right here, and here's the image. You see the arrow pointing down. That's where the negative sign actually comes from, right? So this would be the magnification for a concave mirror. All you need to know is where the object is and where the image is, and you just take the ratio and put a negative sign in front of that. Okay, so we're going to derive something called the mirror equation using that similar picture that we've seen before, but we're going to use that angle that's alpha right there, all right? And so the mirror equation relates the image location and the object location back to the radius of this spherical mirror. All right, so the first thing that we're going to do is go ahead and say, all right, tangent of alpha. All right, tangent of alpha, if we can think about that, is right here, okay, or the alpha is right there. And we see h prime on top, but it's actually, since it's pointing down, we're going to have to call that a negative h prime. And then the adjacent side, if you will, is going to be the entire radius subtracting the image distance, all right? So r minus the q, all right? We also see an alpha right here, and we can make another expression for the tangent of alpha. Tangent of alpha is equal to h on top divided by, now we see the entire distance p, all right? So we see p, then we have to subtract the radius, all right? So p minus the r, because p is bigger than the r in that case. All right, so we could set these guys equal to each other, all right? Where this equals this, all right? And we'll go ahead and do that. So negative h prime over r minus q is equal to h over p minus r. I'm going to have a negative h prime over h, r minus q on top, and p minus r on the bottom. All right. And I'm going to bring the negative sign over to the other side as well. So that means h prime over h is equal to a negative r minus q over p minus r. All right, so h prime over h, if you remember, that's the same thing as the magnification, all right? The lateral magnification, as we can relate that. So in this particular sense, right, we should remember that this is also equal to a negative q over p. All right, because we've said that already, that we have a relationship between h prime over h is equal to a negative q over p. All right, so that just means that we have r minus q over p minus the radius is equal to q divided by p. All right, because we do notice that the negatives cancel each other out on either side right there. All right. So now what we do is do some cross multiplication. All right, I'm going to bring the p up to the top. So p times r minus q times p is going to equal, and bring the p minus r over to this side. That's another qp right there. But then minus q times r. All right, I'm going to bring anything that has an r on the same side, so that'd be a p times r plus q times r is equal to 2qp, because I brought the qp to the other side and added it together. All right. So now we're pretty much almost done. R is times p plus q is equal to 2q times p. All right. And I'm going to bring the qp to the other side on the bottom. And this is equal to 2 divided by the radius. Okay. And so p plus q over qp, that's the same thing as 1 over p plus 1 over q. That will equal 2 divided by r. All right. So there's the derivation of the mirror equation that we're going to see on the next slide. So previously you saw a derivation of the mirror equation, right, which is right here. So hopefully you saw all the math related back to getting this equation right here, but this just relates the radius of curvature of the mirror, concave mirror, to the object location and the image location. Right? If P is much greater than R, then the image point is halfway between the center of the curvature and the center point of the mirror. Well, that's pretty easy, right? If P is much greater than R, let's say it's infinity, right? So 1 over infinity plus 1 over Q is equal to 2 divided by R, which means that Q, because this goes to 0, Q is equal to R divided by 2. That's pretty easy to see, because if you could just imagine that an object that's really, really far away, an infinite distance away, has lines that are coming perfectly parallel, right, to the concave mirror. So when they actually go ahead and bounce off the mirror, they'll all be directed back to the same point, essentially. All right, same point, and here's the center of curvature, but this is halfway, right, because the radius is from here to here. So this is R divided by 2 for this point right here. And this is what we see right here. When the object is very far away, those rays are coming essentially parallel. So when they go ahead and bounce off, all right, once again, we have to talk about reflection. So this angle here, all right, we'll call it theta, even though we should really call this, so we'll call that theta 1. All right, we'll call this guy theta. So that means this is theta 1. So whatever angle that is, if you go ahead and measure that, all right, you'll always get the bouncing off, the reflection of that ray going towards what we call the focal point. And for this situation, F is equal to the radius divided by 2. All right, and it's actually always true, the focal length. And actually, we should give it a little f right there. Let's just use little f. All right, the focal length is going to be r divided by 2. Okay, so distance from the mirror to the focal point is called the focal length. The focal length is 1/2 the radius of curvature. The focal point is just denoted by a point, and it's just a capital F. But the distance, the focal length, is just going to be the radius divided by 2. So the colored beams are traveling parallel to the principal axis in this situation, where you see red, blue, green all coming in parallel. When they go ahead and bounce off the nice curved mirror here, concave, you notice they all meet up right here, and there's a little white speck, or white point, all right, which means they're condensing. The colors of the rainbow make white light, essentially. Okay, so they all come to that halfway of the radius, the focal point. All right, the focal point is dependent solely on the curvature of the mirror. It doesn't have to do anything with the location of the object. The focal point will always be R divided by 2. All right, so it does not depend on the material from which the mirror is made. It's always going to be true like this. All right, which means we could take the mirror equation. Let me go back real quick. All right, that we just talked about, mirror equation. All right, which is 1 over P plus 1 over Q is equal to 2 divided by R, right? And we know that 2 divided by R is the same thing as 1 over the focal length. Okay, so this is the mirror equation again, but just using the focal length of the mirror that we're talking about. Right. So here's another situation, getting rays to be as parallel as possible with each other. When they converge back, they're converging at the focal point, which is half of the radius of this curve. Now, if we go into convex mirrors are sometimes called a diverging mirror, because as you can imagine, when light hits a convex mirror, right? So if you can imagine light traveling this way, when it hits, it's going to bounce off and diverge, all right? Hits down here, it's going to diverge this way. Okay, so light reflects from the outer convex side. So the rays from any point on the object diverge after reflection as though they were coming from some point behind the mirror. What does that mean? Well, you can imagine you can extend this line back. You could extend this line back. And so there's going to be an image on the other side of the mirror, and that's what we call a virtual image. Okay? So the image is virtual because the reflected rays only appear to originate at the image point, which is going to be right here. So here we go again. We have an object in front of a convex mirror. We choose two rays of light. One ray of light is flat horizontal. When it hits the mirror, right, it's going to reflect backwards. But since it's a parallel line, right, with respect to the axis, the primary axis, right, we can understand that if you drew a line backwards, an apparent line back, it would coincide with the focal point, right? And so if we take another ray that's aimed directly at the center point on the other side of the convex mirror, all right? And if it's aimed directly there, then that means the ray will bounce right back to the object, the top, right? And so we, once again, do another apparent dashed line right here. So where these two apparent lines meet, that's where the image is located, all right? It's actually a virtual image. It looks like it's there, but I can't put a screen back here and try to have that image on that screen. So we could say a few things about this, right? That the image that's formed by the convex mirror in this situation is upright, it is virtual, all right? And it's also smaller than the object, because you notice that the height is smaller than the original object height, right? So upright, virtual, because the rays don't actually converge there. If it's a real image, that means we need these orange lines to actually converge, right? And obviously they do converge, but that's where the object was in the first place. And so, so we could see here the image apparent lines actually converge, which means it's virtual. And obviously it is smaller in this case. All right, so if we look at sign conventions, because we got to be careful about how we approach these things, okay? So sign conventions apply to both concave and convex mirrors. We use the same convention for both, okay? So equations used for concave mirror also apply to convex mirror in this case. So what does this mean? Well, if you have, think about what side of the mirror that you're talking about, all right? The front side, as you can imagine, is just in front of the mirror. The back side is just the other side of the mirror, okay? So if you have an object in front of the mirror, well, we say that Q is positive, okay? So let's keep that in mind, okay? If we have a positive Q, that means that the image actually is also in front of the mirror, okay? And this can happen, especially happens with concave mirrors, right? But if we have somehow an object that's behind the mirror, we would actually give a negative sign to that P right there, all right? If the image is behind the mirror, like a virtual image, then that would be a negative for the Q, right? So these are very important. When you're plugging into the mirror equation, you got to make sure you're plugging in the right positive and negative sign associated with that, okay? So the front side is the side where light is going to hit the mirror and then be reflected back, all right? Obviously on the other side of the mirror, there's going to be no light, okay? But P and Q are positive on the front side, P and Q are negative on the back side. And it depends upon where your object is located. That's where you really want to start. All right, and just to summarize all this stuff that we've been talking about, especially when we talk about positive and negative orientation, All right. So we already talked about the first couple here, like object location. All right. We know that it's positive when the object is in front of the mirror. That means it's what we call a real object. Right? It's negative when the object is in back of the mirror. It's a virtual object. And really, we don't have to worry about those until we get more into, well, if you get into reflecting telescopes, right? Where they actually use image lenses and mirrors to go ahead and give us, well, actually, a lens actually uses an image coming off a mirror as an object. And it's kind of gets a little tricky. We don't really want to get there just yet, but that's what can possibly happen with using a lens and a mirror. And a telescope uses two lenses, and sometimes it uses the image of one lens as the object of another lens. So that's where you might get into virtual objects. All right, image location, it's positive when the image is in front of the mirror, as we said. All right, when the image is in back of the mirror, which can happen, that would be called a virtual image, and we use a negative sign for that. All right. Now, image height, this is pretty easy. Image height is positive when the image is upright. We know image height is negative when the image is inverted. Okay. Now, the focal length and radius, right, they're going to be positive when we're talking about a concave mirror. So whenever you have the focal length, let's say here's the radius, the center of curvature, there's the radius, and then there's the focal length, r divided by 2, the focal length. All right. R and F are both going to be positive when the mirror is concave. Okay. Basically when R and F are on the left side of your mirror. When the mirror is convex, we do this, right? The light's coming from this way, but the radius goes kind of backwards, right? There's R, and the focal length is half of R. So it's on the other side of the mirror. That means the mirror is convex, and we actually use a negative for the radius and a negative for the focal length for both of them when the mirror is convex. For magnification, obviously, if it's a positive value for M, the image is upright, and if it's a negative value for M, that means the image is inverted. So it's very similar to the image height situation. Image is upright when it's positive, image is inverted when the image height is negative. And this similar goes for the magnification as well.